Hi, welcome to the video on using integration to find the area between a curve and a line. I'm just going to get straight into it, otherwise this video is going to be super long, but we're building on all of the things that you've looked at in integration so far. So using limits, finding an area underneath a curve, and then introducing a line to kind of manipulate the area that we're trying to find. I don't know if that makes sense. I don't know if that's the right word, but hopefully you know what I mean. So the question would look something like this. So determine the area between the lines with equation y equals x, 4 minus x, that's your curve, and y equals x, that's your straight line. So what we're trying to find is this shaded blue area here. To do that, we could start by finding the area under the curve, which is this blue area here. So that takes us all the way down to the x-axis, and then we could subtract this area of a triangle here. Now I've done that a bit messily, but hopefully you see what I mean. So we're taking out the area of that triangle, which we're just going to use our basic formula for a triangle, for area of a triangle, which is a half base times height. So that's what we're going to do. We need limits. As the question stands, we don't have them as it is. The way we find the limits of the integral, because we're going to need to integrate the curve, is to find where the two lines intersect. So find where the line and the curve intersect. To do that, they're both in the form... Oh, I forgot that I made that really big. This one. They're both in the form y equals, so we can put them equal to each other. I keep doing that the wrong way around. 4 minus x equal to x, and then we want to solve that. If we expand the bracket, put everything on one side, I'm going to just do it this way. So we get 3x minus x squared by subtracting the x. It's now equal to 0. Factorize that again to make it easier to solve. So x would either be 0 or x is 3. So basically where the two lines are intersecting are here at 0 and where x is equal to 3, which would be this point here. We're not interested in the specific, or at least not in this example, we're not interested in the actual coordinate. We don't need the y value. We just need the x value so that we can put it on as them as our limits on the integral when we integrate the curve, which is what we're going to do next. So we're going to start by integrating between 3 and 0 x 4 minus x. Now again, I'm going to expand that out because I cannot integrate it in the form that it's in. I need to expand the bracket first, and then I integrate as normal by increasing the power and dividing by the new power. Now I'm putting it in square brackets because I have limits, so that gives me 4x squared over 2 minus x cubed over 3, and we're putting the limits 3 and 0 on there. To then evaluate between those limits, I put each value of x in and subtract, so I get 4 divided by 2 is 2, so I've got 2 lots of 3 squared. I just quickly in my head just simplified that fraction because I can divide 4 by 2. So I've got 2 lots of 3 squared minus 3 cubed over 3 minus, when I put in 0, everything's just going to be 0 because I've got 2 times 0 squared, which is 0. So I'm just going to put 0 in that bracket. Evaluate that. So 3 squared is 9. I haven't got my calculator to hand. That's not helpful, really. 3 squared is 9, times it by 2 is 18, minus 27 over 3 is 9. So the area is 9. The area underneath the curve is 9. I then need the area of this triangle here. Now we know the base of it. Oh, maybe I do need that y value, really, don't I? The base of it is 3 because this point was 0 and this point was 3. Sorry, this point here was 0 and this was 3. The height, the line's y equals x. So when x is 3, y is 3. So the coordinate here, where the lines actually intersect, because y is equal to x, and we worked out x was 3, then y is also equal to 3. So this has a height of 3 as well. So the area of the triangle area of the triangle is a half times 3 times 3 is 4.5. Now 3 times 3 is 9, divided by 2 is 4.5. And then to find the actual area under the curve, so therefore the shaded area is 9 minus 4.5, which is 4.5. And that's our answer. So we found the area, we found the points of intersection to put the limits on. For other examples, it would be useful. Obviously, we can see this point is 0, 0 from the diagram anyway, but it would be useful to also find this y value as well for finding the area of the triangle. So in this example, we didn't do it explicitly because the line was y equals x, so whatever x is, y is the same. But where the straight line is a bit more complex, definitely worth finding your y value. Then we integrate the curve using the limits and evaluate it using the limits. We find the area of the triangle and we subtract the two things. They're all kind of basic steps for these types of questions. Okay, we'll have a look at a slightly more difficult question next. More difficult because this time the curve is on top of, the line is on top of the curve, or the line is above the curve. So this time our line is y equals 2x. The curve has the equation x minus 3, and we want to find the yellow shaded area. This time we are going to find the area of this triangle. Can I highlight it? So this triangle here is the area we're going to find, and then we're going to subtract the integral of the curve from the area of the triangle instead of the other way around. So we're starting with the triangle and subtracting the area under the curve. So we're still finding the same components, like we're still finding the same parts of the question, but we're just subtracting it in a different order at the end. So we still need to find the points of intersection first. Again, our equations are both y equals, so we can put them straight equal to each other. So x minus 3 is equal to 2x. If I expand that out and rearrange to solve, I get x squared minus 3x equals 2x. Subtract that, 2x over, and then factorize it back. So I get x equals 0 or x equals 5. So this point here is x equals 5. The coordinate, obviously y is equal to 0 because again we're going through the origin here. Use the straight line to find your corresponding y value. So y is 2x, if x is 5, y is 10. We're going to need that for the area of the triangle. The triangle has a base of 5 and a height of 10. So the triangle area is a half times 5 times 10, which is 25. Now, the trickiest part of this question is the limits for the area under the curve, because we can't just use the limits what we're actually subtracting when we subtract the area under the curve is because we now have this triangle area. We're interested in the yellow part, which now kind of looks a strange shade of orange, but you know what I mean. We're interested in this yellow part, which means we have to subtract Oh, that's too big, which means we have to subtract this part here. So we're actually, when we're finding the area under the curve, the limits we're interested in are here at 5, but also here where A is, which is why it's labelled. It wouldn't be labelled if it wasn't important. Yeah, I think that's kind of a general rule of thumb. I'm trying to think of an example where what I've just said is false. Most of the time, let's just say, I don't want to say always, just because that's probably not always true. But usually if something's labelled, then it's important. This A is important. We do need to know that point, because those are the limits of our integral, because we're actually, when we're integrating under the curve, what we need to find is this area here. So to find what A is, to find the X, to find, the X value of A, we know Y is 0 because it's crossing the X axis. We need to find the, what am I trying to say? We need to find the roots of the curve. So my curve is x minus 3. To find the roots, I can put that equal to 0. So again, x is 0, which we can see because it's the curve is crossing at 0, 0, and x is 3. So this A value has an x equals 3, and those are the limits we are putting onto the integral. So find the area under the curve. We're finding the integral of 5, the integral between 5 and 3 of x minus 3. Again, expand that out because we cannot integrate it in the form with the bracket. And then we want to integrate it. So we get x cubed over 3 minus 3x squared over 2. And then we are putting in 5 and 3. Okay, that we're using those limits. We would put in 5 and we would put in 3 and we would subtract them, just like we did in the last example, just like we were doing in the last few examples. I'm not going to go all the way through it, but you would do some more working out here. You would substitute in 5, you would substitute in 3, and then you would subtract those two values, and you end up with an answer of 26 over 3. To finish off, to find the shaded area, we need to do the triangle, subtract the area under the curve, which gives us 49 over 3. Best to leave that one as a fraction. If you put it as a decimal, it's a recurrent decimal. So best to just leave it as an exact value as a fraction. Okay, hope that makes sense. The next type of question you could be asked, and the final one, before we look at trapezium rule, which is slightly different and I will do in a separate video, is finding the area between two curves. So we've done just the area under a curve, we've done the area between the curve and a line, and now we need to do area between two curves to finish it off. And basically what we do is use this formula. So the area of a shaded, the area between two curves can be found using integration, obviously, by doing the integral of f of x, so your first curve, the curve at the top. I hope that makes sense. So f of x is the curve that is above the other curve. So we can, I can't speak. So we can do it two ways. We can either subtract the curves and then integrate the result, or we can integrate one curve and subtract the integral of the other curve. But either way, you're doing a subtraction and an integration. You can decide which order you want to do them in. I'm going to show you examples where we do it both ways. So the first example, we're going to do it by integrating the first curve, integrating the second curve, and then subtracting the results. The second example I'm going to do by subtracting the curves first and kind of simplifying that and integrating the result and putting the limits on to find the area between them. Okay, so it'll make more sense once you see an example, I hope. So here we've got a diagram with part of the curves with equation y equals 5 plus 4x minus x squared, and part of the curve that has equation y equals x squared over 2 plus 1. So the one that's on the top is the one you're going to subtract from. Okay, so that's going to be the first, and then you're going to subtract the line that's underneath. So y equals 5 plus 4x minus x squared is the curve that is above. So that is our first function, and then we're going to subtract the line that's underneath, the curve that's underneath, this x squared minus x squared over 2 plus 1. Okay, and we're going to do it by integrating both and subtracting. We can see what the limits are because they've been identified on the diagram. So x equals 1, x equals 3. So we are going to find the area by integrating between 5 and 1. The first curve, which is 5 plus 4x minus x squared dx, and then we're going to subtract the integral between 5 and 1 of x squared over 2 plus 1 dx. Okay, so integrate it, and we get 5x plus 4x squared over 2, which is just 2x squared, minus x cubed over 3. We're evaluating that between 5 and 1. And then when we integrate that, we get x cubed over 2 divided by 3 gives us x cubed over 6 plus x. And again, we're evaluating that between 5 and 1. This is where it just looks a bit messy. Because obviously when you're evaluating it, you're having to do a subtraction, and then you're subtracting another subtraction from that subtraction. If you follow that, well done. But yeah, it just looks a bit messy. It's not difficult to do, it just looks a bit messy because you're doing a lot of subtraction. So I'm going to keep using a square bracket just to help differentiate between the two. So I'm evaluating the first integrated result. So I'm substituting in 5 into 5x plus 2x squared minus x cubed over 3. I'm substituting 1 into the same expression and then subtracting them. So I get 5 times 5 is 25 plus x squared 25 times 2 is 50 minus 5 cubed is 125. Oh, it's 3 and 1, not 5 and 1. I can't read. Hang on. 3 and 1. That makes it a bit easier. Well, it doesn't really. Just smaller numbers. Okay, let's start again. So 15 plus 3 squared is 9 times it by 2 is 18 minus 3 cubed is 27 divided by 3 is 9, and then I'm subtracting from that what the result I get when I substitute in 1. So 5 times 1 is 5 plus 2 minus a third. So that's my first, that's evaluating my first integral, and then I need to subtract from that the result I get when I evaluate the second integral. So again, substitute in 3, I get 27 over 6 plus 3 minus 1 over 6 plus 1. And then you would obviously work all that out, subtract it all, gives you an answer of 11, which looks very simple for all of the work we've just done. But yeah, that's our final answer. The area between those two curves is 11 units squared, whatever the units are. That's it. Okay, so that's the first way. That is integrating both curves and subtracting the results. Or this second question is more complex because we need to find the limits ourselves this time. And I'm going to show you the other way of do in these types of questions where we can just subtract the two functions first before we integrate them, which is slightly easier. Just less messy, not easier necessarily, because you're doing the exact same things just in a different order, but just a bit less messy. So the first thing we need to do is find the points of intersections of the curve. They've only drawn one curve on the diagram. So we have y equals x minus 2x minus x squared and y equals x squared plus x plus 6. They're both y equals, so when we're finding points of intersection, we can just put them equal to each other and then solve the quadratic that we get as a result in order to find the points of intersection. So we get 0 is 2x squared plus 3x minus 2. That will factorize. I'm going to kind of skip the whole steps of that because you should know how to factorize or use the formula or however you want to solve that quadratic. I'm going to do it by factorizing. I get 2x minus 1, x plus 2 is equal to 0. So x is either a half or negative 2. Those are my limits for my integral. So my area to do part B, so that's part A done. I found the x coordinates of the points of intersection. We don't need the y at all because we're not finding areas of a triangle in this type of question. So it's not useful at all to find the y coordinate. And now we're going to use calculus, so integrate to find the area of the finite region bounded by S and T. So basically, if we were to draw T on there, it would look nothing like that. It would look something like this, where this part where it's intersecting is a half, and this point where its intersection is negative 2, and we're trying to find this area in the middle of them. Okay, so to do that, we are finding the area of the integral between 0.5 or half and negative 2 of the one S is our line that's on the top, is above. So that's the first one that we put in. And that is 8 minus 2x minus x squared minus the line that's underneath, which is our x squared plus x plus 6 dx. I'm going to simplify that first. I'm going to actually subtract those two things first and then do the integration to the result. Hope that makes sense. So what I get is I'm finding the integral between 0.5 and negative 2 of 8 minus 6. So I'm kind of collecting like terms here. Don't forget that this negative affects everything inside the bracket. So I've got 8 minus 6 is 2. Minus 2x minus x is minus 3x. And minus x squared is minus 2x squared dx. And now I can just integrate that one expression without having to integrate both, apply the limits, and then subtract again. I've done the subtraction first. I just have to integrate one expression and then put the limits in. Personally, I prefer this way, but it's good to have both at your disposal depending on the type of question you're being asked. One may be easier than the other, and you can kind of use your discretion, use your common sense to decide which one's appropriate in each situation. So when I integrate that, I get 2x minus 3x squared over 2 minus 2x cubed over 3. I'm going to put the limit 0.5 and negative 2 in there, and then I'm going to evaluate it. So I'm going to put in 0.5 first. I don't need a square bracket now. So when I put in 0.5, I get 2 times 0.5 is 1 minus 3 times 0.5 squared over 2. I don't have a calculator. I just already have the solution in front of me. Over 2 minus 2 times 0.5 cubed over 3 And then I'm going to subtract from that. 2 times negative 2 is negative 4, minus negative 2 squared is 4 times 3 is 12 over 2, which is actually 6. And then negative 2 cubed is negative 8, which times it by 2 is negative 16, which makes this plus, so it becomes 16 over 3. I would substitute, I wouldn't substitute, I'd type all that into my calculator, I'd evaluate it, work it out, and I end up with the area is 125 over 24. Again, leave it as a fraction. That's the most accurate, the most exact answer that you can get. If you start putting it into decimals and rounding, then it becomes less accurate. Best to just leave it as it is, leave it as a fraction. That's it. This is the last slide, yeah. Again, I'll send the PowerPoint alongside these videos, and go and have a look at the exercises. I think there's a test your understanding question. There's not for this one. There was for the curve and a line question, examples though. And then I'm going to make one final video on trapezium rule, which is, I always find it a bit odd the way like the PowerPoints and even the textbook do this in a different order. Like trapezium rule is where integration comes from. Like you can prove integration using trapezium rule, but you can also be asked to use trapezium rule to find an approximate area underneath a curve. So integrating and putting limits on finds an exact value for the area under a curve. Trapezium rule is to find an approximation. I'll put that into a separate video because this one's already quite long. Yeah, but it's a really popular exam question, and once you get your head around it and do a bit of practice of trapezium rule, it's very easy marks, really easy marks to pick up in your exam. So definitely worth checking out. I'll do that one tomorrow and upload it for you. But yeah, I hope this helps. As always, let me know if you have any questions, and please go and work through some of the exercises from the textbook, and even on integral maths as well. There'll be further videos and things to help you on integral maths too. Okay, thanks for watching and listening, girls.